So there's several other things we can do with a list. So for example, if I have a game and I would like to be able to keep track of the high scores, I may need to sort the list. So every time a new score is achieved, I need to find out where that new score should go in terms of a list of previous scores. I could also, for example, play a song. So I may have two different lists. I may have a notes list and a duration list. So I go through, and each time I pull out a value from the notes list and I play that note for whatever corresponding duration is in the other list. So let's actually try this. Consider the two sections of code that you can see on the slide now. At the top is the program that's actually calling our new block called play song, and at the bottom is the actual play song block. So what play song will do is take two parameters. The first parameter is a list of notes, and the second parameter is a list of durations. So for example, the notes are 67, 65, 67, which are certain notes that we play, and the corresponding duration for each of those three is 0.15 seconds. So every note has a corresponding duration in the other list. So in this case we have two lists, but they have some relation because one is a note and the other is the duration in which we play the note. So in this case, we're calling play song two times because we have a repeat two. And what play song does is pass these three notes and these three durations off to play song. We rest for 4/10 of a beat, and then we do that twice and the program ends. So the interesting thing then is, what does play song do? Well, if you look at the bottom section of this slide, again, play song takes in two parameters, a notes list and a durations list. And initially we're setting our index to 1, so we're going to be able to loop through every note and every corresponding duration. So we're repeating through the length of the notes, and I'm making a call to the existing play note block. So the particular note that I'm playing is being pulled out of notes. So the item index of notes represents one of the three notes that I'm playing, and the for part of the play note represents the duration. So you can see item index of duration as well. So for each one of those three values, or three indices of notes and duration, I'm pulling out a particular index, playing that note for a particular duration. For example, when index is 2, the note that I'm playing is 65, and the duration that I'm playing is 0.5, which is, they're all 3.5, but it would be the second one in that list. So that's how I'm playing those notes, and then I'm updating the index by 1 each time so that I can move through the next note until I've exhaustively played all of the notes in the notes list. So one of the things you may want to try is see if you could figure out what song this is and post on Piazza to see if we can find out who the first person is in this lesson to figure out what song we're trying to play here. So Snap provides a block called contains, and contains will pass back a Boolean value of true or false whether or not the item that you're looking for is actually contained in the list. So that just tells us whether or not that item is in the list. It may be useful to actually know where or what particular index that item appears. So if we wanted to write that ourselves, we could create our own search block that would loop through all the elements of the list, and that block would take in a parameter representing the item that I'd like to find, as well as the list that I'd like to search through. So I'm looping through the entire list, and if I particularly find where there's an indexed value in the list that is equal to the item I'm searching for, I immediately report back through my block the index that I found where item was located. So you can check out the English here on this slide that explains how that's done, and we'll look at the code on the next slide. So if this item is not found, we want to make sure we return a value of -1. So the code that you see here at the very top also accomplishes in Snap what we just described in English. So I have a block called search where there's an item that I'm searching for, and there's a particular list that I'm looking through, and I have my loop or my index counter. I'm repeating through all the elements of list. So you should be seeing a common pattern in the way that we process lists. There's some kind of list counter, index or counter or some other named variable that we're initializing to a certain location, in this case the beginning of the list at 1, then we're repeating through the length of the list. So this pattern we've seen a few times. And so inside the body of this repeat loop, I'm trying to find if the item that I'm interested in, that was passed in as a parameter, this variable or this parameter called item, if it happens to be equal to one of the index values inside of the list, then I immediately end my block and I report back the index where I happen to find the item in the list. If I don't find it at a particular index, I increment my index and move on to the next item in that list. And eventually, if my list ends and I've not yet found that item, it means the item must not be in the list. In that case, I report back a -1. So that's indicating the value doesn't exist, because -1 is not a legal index value for a list in Snap. If you look at the very bottom of this slide, you can see how we're calling this particular block. So the first call is searching for the number 100 within a list that has the values 1, 10, 100, 1,000, and 10,000. So obviously the number 100 is in this list. So what should be returned here is the index where 100 was found. So in this case, we find 100 in index 3 in this first call. Now the second call will return a -1 because the item that we're searching for is not in the list. So I'm searching for the value 20, but that does not appear in any of the list values. So I eventually reach the end of the list when I'm performing the search block, and I return a -1 because 20 does not exist inside of there. So the topic of searching and sorting is very important in computer science. There's been many books written about this, and it drives all kinds of interest in various contexts in which we do a computation. So it's a topic of deep study in computer science. And so we will revisit this idea, or both of these ideas, of searching and sorting, and we'll study that in a lot more detail when we come back to this in the context of the big idea of algorithms.